All right, in this example, we're going to find the volume of the solid above the half cone, z equals square root x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals z. So it would be helpful with this to get an idea of what the sketches of these pictures look like, so that we can help set things up in the future. So if we take a look at, say, the cone that we're taking a look at, well, we've got this z equals the square root of x squared plus y squared. Now we can picture that this isn't actually a full cone, it's a half cone, because z is going to be strictly positive values since it equals a square root, well, non-negative values since it equals a square root. So we're only going to have an upper half cone. And then what we can think about is we've got x squared plus y squared in that square root. So then whatever the z value is going to basically be the radius of the circle of all of those cross sections. So like when z is 0, we have the equation x squared plus y squared is 0, which is just right at the origin. When z is 1, we have x squared plus y squared is 1. So we would come out. And that cross section when z is 1 would be a circle of radius 1. And as we keep increasing z, the radius of that cross section circle is just going to keep increasing. So we're going to see that we have this nice round upper half cone right here. Taking a look then at the sphere that we have, we've got x squared plus y squared plus z squared equals z. Now, it would be nice to be able to identify the center and the radius of that sphere. So let's go ahead and move the z over to the same side. And then let's take this chunk of the two different z parts and complete the square so that we can see the z coordinate of the center point. So on both sides of the equation, then we're going to add that b over 2 squared to complete the square, which in this case b is -1. So we're adding 1/2 squared to both sides. So we've got z squared minus z. We'll have plus -1/2 squared equals -1/2 squared. So then we have x squared plus y squared plus z squared minus z plus 1/4 equals 1/4. Now the reason we did this is now a perfect square if we factor it, where we're going to have z minus 1/2. It's that b over 2 term squared. We can double check that quick, right? If we do this squared, we'll have z squared minus 1/2 z minus another half z, which is why we have -z, and then plus 1/4 from the -1/2 times -1/2 equals 1/4. So then we have our center is at 0, 0, 1/2, because it's the x minus the x coordinate, y minus the y coordinate, quantity squared, and then z minus the z coordinate, quantity squared. And then my radius is it all equals r squared, so it's the square root of 1/4, which is 1/2. So we've got the center of my circle is right at 1/2. And then when we draw that sphere, then it has a radius of 1/2, so it's going to have intercepts at the origin and at 1. And so then what we can see when we draw this circle, let's actually just go ahead and I'll just change my scale of what I had on the z-axis to be able to see our picture a little bit clearer. So let's just go ahead and put like 1 up here. It doesn't really matter for the cone. And then we'll put a half here. So then my sphere comes down and it's like this. So the shape that we're looking at then has a little cross section right here. And remember, we're looking for above the cone and below the sphere. So really then what we're looking for is kind of this inside part where we're kind of inside the sphere, or we're inside the cone and underneath the sphere. So that's the part that we're looking at right there, is what we want for our volume. So we have to decide then how we want to go about solving for this volume. Now, one of the things that I'm going to point out is both of these equations are going to be very related to spherical coordinates, right? If we take a look at our z component, we're going to have a lot of simplification that happens. And if we take a look at our sphere, when we put it in spherical components, a lot of simplification is going to happen. So let's try and see what those equations look like in spherical coordinates, and then try and set up our integral from there. So let me scroll down a bit here. Let's try and take a look at these equations in spherical. So let's look at the cone first. So our cone was z equals the square root of x squared plus y squared. So if we make all of our different replacements, well, z is rho cosine phi. X is rho sine phi cosine theta. So that's going to be quantity squared. Y is rho sine phi sine theta. And that's also quantity squared. And that's all in a square root. So we've got rho cosine phi equals rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Which at the moment doesn't quite look better, but be careful to notice what we've got here is we've got cosine squared theta plus sine squared theta, where they both have the exact same coefficient, rho squared sine squared phi, which means if we were to factor out that rho squared sine squared phi, the cosine squared theta plus sine squared theta would just sum up to 1. So then what we're going to have when we add those together is we'll just be left with rho squared sine squared phi, and then that's all under a square root, so we're just left with rho sine phi. And over here we have rho cosine phi. So if we take a look then at simplifying this equation, well then what we're looking for here is we could consider rho being 0. One of the ways to kind of see this is to take this and move everything to one side. We could have like rho cosine phi minus rho sine phi, oops, not theta phi, equals 0. So then factor out the rho. So we could have rho equals rho equals 0, or we could have cosine phi equals sine phi from this cosine phi minus sine phi equaling 0. Taking a look at what this would look like, well, this point right here, rho equals 0, is just the origin point. So that's not the full equation of our cone. So then we can focus on this cosine phi equals sine phi part and look for phi values that make that true. We can think about which quadrants we would be taking a look at here. So we need cosine and sine to have the same sign, meaning positive or negative. So we're either going to be in the first quadrant or we're going to be in the second quadrant or in the third quadrant. Either they're both positive or they're both negative. And the reference angle where those two are equal to each other would be pi over 4. So we could have phi as pi over 4, or phi is 5 pi over 4. So that's in the first quadrant, or then coming all the way over to the third quadrant. However, we do have a restriction on phi, where phi is strictly between 0 and pi. So that gives me a unique solution then. We just have phi equals pi over 4. So then if we think about what we're going to end up wanting for our cone, is that phi equals pi over 4. Essentially then rho is left to vary and theta is left to vary. So it's basically just fixing this angle of phi that we make, and then we swing it. We can let rho vary through all its positive values, and then it will swing all the way around to create the full cone. So the rho equals 0 is really just a redundant equation for this formula. So this is really redundant. So we can just keep the formula of phi equals pi over 4, which is what's representing the cone here. So then we can take a look at our sphere. Let's go back to looking at the sphere. Let's do it from right here, where we just had moved everything to one side. We don't really need the completed the square version because that just helped us graph it. Rather, if we think about plugging in things for spherical coordinates, using that top one is going to be better. So we've got x squared plus y squared plus z squared. Oops. So x squared plus y squared plus z squared minus z equals 0. So then if we sub things in, well, this first part, x squared plus y squared plus z squared, is just rho squared, and then z is rho cosine phi, and then that whole thing equals 0. So let's pull a rho out. So we've got rho times rho minus cosine phi equals 0. So this would either give us rho equals 0 or rho equals cosine phi as a function of rho. Again, rho equals cosine phi. Well, if we pick appropriate phi values, such as when phi is pi over 2, we'll get rho equals 0. So this is redundant. So we really only need rho equals cosine phi. So what I want to do then is think about those bounds for all of my different functions, for what we need these different variables to do, where they need to vary from. So let me just really quick sketch that picture again one more time here. So we had our sphere, and then we had our cone. And so the sphere is rho equals cosine phi, and the cone is phi equals pi over 4. So then we really want to think about bounds for rho, phi, and theta. And remember that we're trying to be on the inside here, the inside of the cone underneath the sphere. So if we think about for rho, well, rho is that angle measurement, the length measurement, so the length from the origin to any point on this. And so if we think about where we're going from here, well, really any point on this goes from the origin up to kind of the top portion of this shape, which is defined by the sphere. So we're really going from 0 to the sphere, which is cosine phi. Right, at every point here, we either go from the origin up to the sphere. What we have then for phi is we want to think about, well, to trace out this full solid, what angles do I need to come out from the z-axis to measure? So we want to come all the way through. We want this to be a solid figure, so we'll start with phi equals 0. That gives us that z-axis. And then we go all the way to the edge of the cone, which is phi equals pi over 4. Then lastly, theta takes that shape that we just created and it figures out what angle we want to swing it. So how much of that shape do we need? And we need to do a full rotation in order to get the full 360 degrees of that shape. So we'll go all the way 0 to 2 pi for theta. So now we're ready to set up our integral. So when we set up our integral, we're going to have that the volume is a triple integral. If we do rho on the inside, then rho goes from 0 to cosine phi. Then phi goes from 0 to pi over 4. And then theta takes that and swings it from 0 to 2 pi. And we're doing this as a d rho, d phi, d theta integral. Remember, normally if we were in rectangular coordinates to find the volume, we would integrate 1. However, since we converted to spherical coordinates, we need to add that scale factor for spherical coordinates, which was rho squared sine phi. And now we're ready to integrate. Notice we're doing a rho integral first. So we're going to end up with rho cubed over 3, all still just times sine phi, because we treat sine phi as constant. That's going to get evaluated from 0 to cosine phi. And then this is still in an integral from 0 to pi over 4, and from 0 to 2 pi, d phi d theta. So now if we plug into that integral, we're going to end up with the integral from 0 to 2 pi, 0 to pi over 4. We'll have a third cosine cubed phi sine phi, d phi d theta. Notice we're doing a d phi integral now, so we've got cosine cubed phi times sine phi. So hopefully taking a look at those two trig functions, they're related by the derivative, so a u substitution is probably a good choice. Taking a look at which u substitution to do, it's probably a good idea to do u as cosine phi, because then du is negative sine phi d phi. And I have that sine phi d phi, so that's going to be a nice substitution then. If we figure out those bounds, we had when phi was 0, we're now going to have u is cosine of 0, which is 1, and when phi was pi over 4, we're going to have u is cosine of pi over 4, which is square root 2 over 2. So all in all then, we're going to get an integral 0 to 2 pi. We now have our new u integral, which will go from 1 to square root 2 over 2. And then we're going to have, we'll introduce a negative from the du. So we'll have negative 1/3 u cubed. And then sine phi d phi gets replaced with du and the negative, which we already introduced. And then this is still d theta. So then we're going to end up with a negative 1 over, we'll end up with a 12 u to the 4th. That's going to get evaluated from 1 to square root 2 over 2. Then this is still in 0 to 2 pi d theta. So then taking a look at what we have now, plugging those in, we'll have the integral 0 to 2 pi. Square root 2 over 2 to the 4th. Square root 2 to the 4th would be 2 squared. So we'll end up with 4 over 2 to the 4th is 16. We then will have minus, plugging in 1 to u to the 4th is just 1. And this is all d theta. 4 over 16 is really just 1/4. So we're going to end up with the integral 0 to 2 pi. We'll have a negative, 1 over 48 plus a 12th. When we evaluate that, we'll end up with that negative 1 over 48 plus a 12th, all times 2 pi. So we'll end up with like negative 1 over 24 plus a 6th times pi. If we do combine those, let's think a 6th is going to end up being 4 over 24. So then we'll end up with 3 over 24 pi, which 3 over 24 is an 8. So we'll end up with pi over 8 as our final volume for that solid.